Welcome to my channel AI Basics with AK. It's been almost a couple of months since I have released a new episode because I was occupied on personal things. So here is season 3. We have discussed so far about what is statistics, types of data, descriptive statistics, data visualization, basics of probability, and today we will discuss about probability distribution. So let's see our episode 6 of our season 3, which is introduction to statistics, and episode 6 is probability distributions. Before going into the episode 6, let's recap what has happened in episode 5. In episode 5, we have learned about three major things, which is sample space yes, which is nothing but all possible outcomes. Say, for example, in a pack of cards, how many possible outcomes are there? It has 52 possible outcomes, right? And we are going to predict an event. Say, for example, what out of 52 cards, how many red cards are there? 26, right? And outcome will always be only a single result, because we will be drawing only a single pack, a single card, but not all 26 cards. So what is the probability of that outcome? It is nothing but number of favorable outcomes, which is nothing but 26. And what is the total outcomes? Which is 52, which is 26 by 52, which is nothing but 0.5. A similar example, you can see it here. Make sense? Now, this is only a single trial. So here you could see the same thing, probability of getting heads from tossing a coin. How many possibilities are there? Two possibilities, same, two possibilities. And how many heads will be there? It is only one head. Outcome will always remains as 1, so that will never change. So what is the probability of heads? It is only 1 by 2, which you can see it here as 0.5. Now this is just a single trial. What will happen if we roll many times? Is there any pattern? Here I am trying to showcase an example of rolling a dice. Now now if I'm rolling only once, it's just a random distribution at a back end. You can see here, okay, there is some possibility that 1 can happen, 2 can happen, 3 can happen, 4 can happen, 5 can happen, 6 can happen. But ideally, when we see it out, any pattern can happen, right? But why there is an uneven distribution when we are rolling only 10 rolls? Because when we are doing only 10 rolls, okay, and we do not have any historical data, we can you roll dice only once, okay, only one has come once, and then the second has appeared twice, maybe third has appeared 4 times, maybe fifth has appeared 4 times, and fourth has appeared 1 time. So accordingly it has constructed this pattern. But as you increase the trials, the distribution looks more and more even as an uniform distribution, which you can see it here. As we roll even further to 500 rolls, you can see that distribution is almost even pattern that you could see here. Make sense? You could see the distribution is almost pattern, like every dice, okay, showcases almost equal, like 80 to 90 times it appears when you are rolling almost 500 rolls. Make sense? So what is this called distribution? This distribution, you can see that it is very uniform. This is called a uniform distribution. Why it is uniform? Because each dice can appear as many, it has equal number of options to come. So when we see the probability here, it is, even though it is one heads as one and tails as one, it has equal probability. So similarly, each face of a die has an equal or uniform probability to appear. How do we come up with this? When we roll many times. So it comes from the historical pattern. Got it? And what is this pattern? It is called as, we call this pattern as probability distribution. So earlier we came up with this probability based on some assumption, assuming that this dice is fair dice, this coin is a fair. So in that case it is true. But when we have enough historical data of 500 rolls, you can get that real world how much each face of a dice can come up with. Make sense? Now this is a uniform distribution that we can see in it out, but in generally probability distributions has two types of distributions. One is discrete distribution, second is a continuous distribution. Discrete, that we have seen it out here, has something like, it has individual kind of a thing, like there is nothing between 1 and 2, so it's head or tails or 1 2 3 4 or 5 or 6, which is finite or countable. But continuous distribution is like a height, it's 4 feet, 4 feet 1 inch, 4 feet 2 inch, 4 feet 3 inches, etc, etc, etc. Got it? Now let's unpack three important distributions at this point of time. Uniform distribution, which we have seen it earlier. It is rolling a dice, a random pick, all outcomes can come equal. It's like a flat histogram. Normal, it is like more continuous, because most of the times it comes around some mean of the distribution. I'll come up with this, okay, more, okay, in the next episode. Binomial distribution, it is like a discrete, but it is more like successes, because it has only like two possibilities, either success or a failure. So it showcases, okay, a hill shaped of distribution at discrete points. Got it? So let's understand what is uniform and why it is called as. Uniform means it is almost same, everything is equal. Normal, why it is called normal? Because this is the most common pattern that we will see it in nature. And when we, in data science, most of the assumptions comes out that all distributions are normal, even regression, everything. So that's the reason we will discuss more about this normal distribution in the upcoming episode, in episode 8. Because between episode 7, 6 and 8, there is a most important episode, episode 7, which is CLT, which needs to be learned before we understand what is a normal distribution. And there is a binomial distribution. Why bi? It is nothing but it comes from two outcomes, which is called as a bi, because it has only a success or a failure, okay, and it comes from a nominal kind of a thing, because we are counting those success or failure events kind of a thing. Got it? Now let's visualize these pieces. Now, sorry. Okay. Now you can see that there is a normal distribution. Okay, there is a probability density function of a normal distribution. As you increase the number of sample sizes, like number of data points of a normal distribution, you can see that, okay, it looks like something like an, okay, it looks like something like a bell curve. So that's why it is called something like a normal distribution. In most of the real world, when we are trying to predict for one outcome, what is the height of one child, mostly, okay, we will take the average okay, if we don't know about it, we will take the average height of a one class. So that's why it is called as a normal distribution, because there is a normal pattern. When we see it outside, we try to substitute with an average kind of a thing. And it also and sometimes it is called as a bell curve, because it looks like something like a bell kind of a thing. Okay, now let's see another important piece, which is a uniform distribution. In a uniform, you can see here, it's always uniform. Okay, when we change, okay, I have to change it again here. The uniform always looks like a flat layer. Okay, that we have seen it already earlier, which is in our rolling a dice. Now when I change to binomial distribution here you can see that when binomial distribution, it is a discrete kind of a thing. For each and every sample size, when we are increasing, okay, we can see that the probability of the success or a failure rate is also changing. But most important factor that you can see that even binomial has a normal kind of a distribution when we start increasing the sample size, even the binomial distribution. I know, okay, jumping from uniform to normal distribution is slightly confusing at this point of time. So in the next episode, we will explore more about central limit theorem, which is shortly called as CLT. But let me just recap again, what is the prime difference between uniform, normal, and binomial. Uniform distribution, when we can say that, okay, all outcomes are equally possible, like rolling a dice 1 can come, 2 can come, 3 can come, 4 can come, 5 can come, 6 can come, with equal chances. But what about height of a child? Every height of a child is very different. But however, if you want to guess a height of an unknown child, you substitute with and some central tendencies that we have learned in our initial episodes of our statistics, either with mean, median kind of a thing, right? So these are very normal patterns that we'll accept outside, and when we see the distribution, you can see the distribution of the entire class ideally is in a form of a normal curve, which is called as a bell-shaped curve. So it is called as a normal. Here, instead of normal, when we are having only two outcomes, it comes as a binomial. But in the next episode, that is in episode 8, we will explore more about normal distribution, because which is much more important for our fundamental understanding. So with this, I am closing this episode 6, and there is no homework for this episode 6 until 6th, or even for 6th episode there is no homework. But from episode 7, that is from central limit theorem, which is a precursor to our normal distribution, we will start, okay, attacking our homeworks with an increasing difficulty level from that episode onwards. So thank you for listening to this episode, and see you soon for the next episode. Have a nice day.